All right, welcome to our first online lecture for this general geology class. This is sort of the basics of chapter 1, and what we're going to be covering here for the most part is plate tectonics. It is kind of the biggest part of geology, kind of the unifying theory. And so we're going to kind of start big here with this class, and then we're going to sort of break it up into the smaller pieces. So that analogy that I hopefully have used in class, or I've told you up until this point, is that geology is sort of like a language, and we look at rocks, and they're kind of like the words of a story. So if we can identify these rocks, we can read the words, and then we can put them together, start making sentences, and figuring out what's happened in the past by being able to read these rocks. Well, this chapter is basically like, here's the summary of the book. Here's what the rocks tell us about what's going on overall, kind of looking at our whole planet. So we'll talk about plate tectonics and kind of the processes, and starting with sort of the makeup of the Earth itself and all the layers that it has and this sort of thing. So we'll start with that. So here we have the Earth. The Earth is broken up into several different layers. How we know these things exist, we'll talk about later on in the class, actually much later on in the class. We've never been able to drill this far down into the Earth, and just as a preview, the reason we kind of know this is we use earthquakes, kind of like how we use sonar under the ocean. An earthquake is sort of like a ping when it goes off, and we can listen to those seismic waves and measure those seismic waves as they travel through the Earth, and they will reflect off these different layers, and they'll kind of carry the properties in those waves of these layers, and so we're sort of able to distinguish where these layers are and kind of what they're made out of. But anyway, so here's the Earth. At the very, very tippy top outer layer, it is very thin compared to the rest of the Earth, we have the crust. The crust is usually about 5 to 60 miles thick. Not very thick, and these are all in kilometers, so I apologize for that, but not that there's anything wrong with kilometers. But the radius of the Earth here you can see is 6,300 kilometers. Well, the crust is just, 10 to 100 kilometers thick. Very, very thin compared to the rest of the Earth. So thin that, you kind of need to blow it up here and amplify it to get a look at it. And then below that, we have the mantle. And then below that, we have the core, which there's an inner and an outer core. So let's start with the crust. With the crust, it is the outermost layer. It is thin, as I said, and it's the only layer we see, right? There's nowhere you can go on the Earth and be like, oh, look, I'm on the mantle. That doesn't exist. You're always on the crust. There are two different types of crust. There is oceanic crust, and there is continental crust. And they are different. Let's talk about oceanic crust. Oceanic crust is thin compared to continental crust. You can kind of see that represented here. This is the piece of oceanic crust. Here's a piece of continental crust. It's thicker than the oceanic crust. Oceanic crust is denser, so it's heavier. In fact, to the point where when oceanic crust runs into the continental crust, oceanic crust tends to be pushed underneath continental crust. Continental crust is thicker and it's less dense. The way I like to kind of give an analogy or a metaphor to the continents on the surface of this planet is they're kind of like ice cubes floating around on the top of the rest of the planet. They're never really going to want to go down. They're made out of stuff that's not as dense as the rest of the material of the Earth, so they kind of just float around on the surface. So, beneath the crust, we have the mantle. The mantle is made out of dense silicates. We'll talk about what silicates are later on. The crust is also made out of silicates. It is hot, soft rock. It's not molten. A lot of people think that the mantle of the Earth is molten because magma and lava will come out of it, but that's not the case. It's actually hot, soft rock, kind of plasticky if you sort of want to think about it that way. Not quite gooey, but approaching what you might call gooey. However, there are a few molten spots, especially as you kind of get closer to the surface. Things can tend to melt a little bit. But for the most part, it's hot, soft rock. It's not molten. Once you get to the core, however, it is mostly iron, and the inner core is solid. The outer core is a liquid. We'll talk about how we know that later on. Oops. Yeah, that's all we need to know about that at this point. Liquid outer core, solid inner core. A way to think about the Earth is, and it's not just the Earth, a lot of different, this is sort of a feature you see in a lot of the galaxy, the solar system, is that the lighter material is on the outside, the less dense material is on the outside, and as you go in, things get heavier, things get denser. So if you take a look at the periodic table, right, the elements on the periodic table that have the really big numbers on them, those are heavier elements. You will find them farther down inside the Earth than you usually will find them on the outside. The stuff with the really small numbers on the periodic table, you will find more on the outside. So, some of you have probably heard, that the Earth is built like this. You have this crust and mantle and core. However, those are mostly based on chemical properties, what the stuff is made out of. There are also mechanical properties to the Earth, and we break up in these other layers. The core sort of stays as it is, and the mesosphere is very similar to the mantle. But on the outside, I want to talk about this stuff, the lithosphere and the asthenosphere. Can you say that? Lithosphere, asthenosphere. And what is that? Well, the lithosphere and the asthenosphere, they basically act differently. The lithosphere is the part that's rigid. It's the uppermost part of the mantle and the crust. This lithosphere acts like a solid. It moves around. It's basically more the surface of the Earth that gets pushed around by the asthenosphere, the part of the mantle that's convecting and moving around, and the lithosphere floats on top of it. The way to remember that is litho means rock, so it basically means solid. It means rock. I think that's Greek. Anyway, so lithosphere, rigid on top. It's the crust and a piece of the upper mantle, so it's not just the crust. Otherwise, we probably wouldn't call it this. We just call it the crust of the mantle. But since they act differently, we have lithosphere and the asthenosphere. So the asthenosphere, kind of plasticky, as I mentioned, as the mantle is. It's below the lithosphere, and it's sort of the mid-upper mantle. In fact, the lithosphere doesn't even go down that far. It's really just the upper sliver of the mantle. Most of the mantle is the asthenosphere. So the asthenosphere flows around ever so slowly. It carries the lithosphere along, it pushes it along, and at the speed at which it does it is about 1 to 14 centimeters a year. That's about as fast as your fingernails grow. It's about 1 to 14 centimeters a year. I think your fingernails grow at about, it depends per person, but it's about 5 or 6 centimeters a year, I think. And we call this motion, the way the lithosphere floats on the asthenosphere, we call that plate tectonics. So this is a video I will post into Canvas. I won't play this right now, but it's kind of the first of 2 videos I want you guys to watch. Really good. Talks about continental drift and plate tectonics. Go watch that right now, and then come back to this after you're more educated. So you've now watched that. Let's talk more about plate tectonics. It sort of revolutionized the study of geology. Everything started to make sense. All these big observations we were making about mountains and rocks that we see in different parts of the world and why they're the same and how they could be that way. Plate tectonics sort of answered those questions for us. They made sense of it. One of the neater things about plate tectonics is it's a recent theory. It was sort of verified in the 50s and 60s. The original idea, which was continental drift, which is kind of the basis for plate tectonics, that wasn't thought up until about 1915, which is around the time we figured out how to make planes and everything. But if you learn about the history of other sciences, most other sciences, the majority of those sciences, they were established and well known uh, far before the 1900s. Um, theory of evolution in biology. The theory of evolution in biology is very similar. Evolution to biology is what plate tectonics is to geology. Well, Darwin's book didn't show up till what, the 1830s, I think, and I might even be wrong about that. I have to go check that. But most of science was kind of, we know most basic things of most sciences, most subjects, far before the 1900s, but then we figured out plate tectonics far recently. And you can go find old textbooks from the 40s and you can start reading about how they talk about mountains in those textbooks, and they almost kind of trail off because they don't quite know like where mountains are coming from and how mountain building happens, or why Africa and South America fit so well together if you were to cram them together. Like these things are sort of touchy-feely, and we're not really sure how that works yet. And it's neat to, if you're ever in an old bookstore or something, go to the science section, see if you can find an old used geology textbook, flip through there. It's quite interesting. Some stuff they knew really, really well, but this big unifying theory of plate tectonics is fairly recent. So, what is it? What is it? So if we take the lithosphere, right, that upper part of the Earth, if we look at it closely, it's broken up into pieces, kind of like a broken eggshell on top of an egg. And these pieces that we call plates, they're shifting around ever so slowly. Let me change the map real quick. So here are the major plates kind of labeled out on this map, and there's a lot going on this map. There's these different boundaries listed down here, and we'll talk about what those are here in a couple seconds or a couple minutes. But here are all these plates, and they're all kind of shifting around on top of the surface of the Earth relative to each other. So the Pacific plate's kind of moving this way. North American plate's moving ever so slightly to the west. So let's think about this. So the North American plate is moving to the west. We're sitting on the North American plate somewhere around right here, right? Right in here is where Arkansas is. If that's moving about as fast as your fingernails grow to the west, let's just say 6 centimeters a year, where the seat you're sitting in, last year when I was teaching this class, the seat you were sitting in was actually 6 centimeters to the east. Or even the chair you're sitting in last year was 6 centimeters to the east relative to the rest of the entire planet. So kind of a nifty thing. All I wanted to show with this map is kind of talk about continental drift, because the first idea that was thought up was continental drift by a guy named Alfred Wegener. And you look at you have these observations about how, hey, Africa really fits well against South America, and this part of Africa really fits well up into North America, and what's with that? Why does Greenland fit well up here against Canada? What's going on? So he proposed this theory of, hey, the continents shift around and kind of float around. And then later on, when we started getting the technology to go drilling and look at the bottom of the ocean and collect samples from the bottom of the ocean, that's when we were able to say, hey, okay, this continental drift is a real thing and it's happening, and the mechanism is this whole idea of plate tectonics. So there are boundaries between these plates. You'll see that there's different symbols for some of these boundaries. What's happening? There are 3 basic different things that are happening, or that can happen, at these boundaries. And we call them divergent boundaries if they're spreading apart, convergent boundaries if they're coming together, or transform boundaries if they're moving side by side. So those are the 3 main plate boundaries. I'll go through them fairly quickly. So divergent boundaries, they're moving away from each other. You find this on the ocean floor. You find it at the Mid-Atlantic Rift or Ridge. So here's the Mid-Atlantic ridge. There's actually a mountain chain down here, and it's where new crust is being created. You have upwelling from the mantle. It breaks through the surface of the crust, of the oceanic crust, and it solidifies, it cools into an igneous rock, and it sort of creates this, what's the word I'm looking for? Conveyor belt effect for creating new oceanic crust. So it upwells here, it cools off here as new rocks, and then it moves away from this ridge ever so slowly. You can see there's another ridge right here. You can follow it all the way around. So these ridges extend all the way around the planet. And Iceland, you can see up here, Iceland is actually where that ridge comes out of the water. So that's a divergent boundary. It is where new crust is created, new oceanic crust is created. So another way to look at it, mid-oceanic ridge here, oceanic crust going all the way out to the continent. If you were to drill here and take the ages of these rocks, you would find that they get older as you move away from that ridge. And that's what we found out in the 50s and 60s. And we went, oh, holy cow, oceanic crust is being created at these ridges, and then it gets pushed out as it's created, and it moves the continents around with them. So, I always like to share this map. I think it's a really cool map. What are you looking at? Here's North America. You're looking at a map of the world. Here's North America, South America, Africa, and so on. And what you have here is you have those mid-oceanic ridges drawn out, those divergent boundaries drawn out, where these black lines are. The colors correspond to the age of the sea floor. So the hotter the color, the younger the sea floor. So when it's close to the ridge, it's very young, it gets pushed out and gets older and older and older and older and older. So, fun fact, the ocean floor at the bottom of the Gulf of Mexico is some of the oldest ocean floor on the planet. It's about 200 to 250 million years old, which sounds really old, but if you compare that to the rocks on the continents are usually much older than that. The oceanic crust, like I mentioned before, it's denser, it's heavier. Eventually, it will start to get pushed underneath the continents, get subducted, and melt back into the mantle. And when that happens, we have a different kind of boundary. That tends to happen at convergent boundaries. So here's our oceanic crust converging with the continent, and it gets subducted, pushed underneath that continent to come down here and eventually join back with the rest of the mantle, or some of it may even melt and create volcanoes. If anybody's ever flown over to Seattle, well, one of the neatest flights I think I've ever been on is if you fly into Seattle, you will pass this chain of volcanoes, and you can look down this chain of volcanoes for, I don't know, 100 miles, 150 miles, 200 miles, something like that. And you can see volcano after volcano after volcano after volcano, and you're literally seeing where the oceanic crust has been subducted, and it's melting and coming back and creating this line of volcanoes along the continent. Excuse me. So, this is a continental oceanic convergent boundary. You can also have it where continents collide with each other and push up big mountain chains. That's what the Himalayas are, where India is collided with Asia. You can also have oceanic crust that hits each other and one gets subducted, and that's where you'll find island arcs. I believe Japan's a good example of that. Then there's the third one, which are transform boundaries. This is just where they're sliding past each other. So here's a simple drawing of a divergent boundary. Here's a simple drawing of a convergent boundary where one plate's getting subducted underneath the other. And then there's a transform boundary where it's just side by side. No magma is generated, just broken rock, just a bunch of faulting. And you'll see this a lot along divergent boundaries where it kind of exists next to them. So, Here's another video I want you to go watch. Pause this lecture, go watch this one if you can. However, if you like watching this on your TV or whatever, you can always watch this after the fact. This is just kind of a cool thing. It's kind of the what's happened with the continents over time. It's a fun video. There's kind of a lot there. This is my favorite YouTube channel. I highly suggest watching this, and honestly, just go binge that YouTube channel if you're into geology and the age of the Earth and all the things that have happened in the past. They've got really, really cool stories. It's run by people who are paleontologists and get advice from other paleontologists, and it's also sort of a subsidiary or partner with PBS. Anyway, so let's move away from real quick from plate tectonics, and I just want to briefly jump into the rock cycle. This is a fun little drawing I found. And so let's just cover this real quick. Hopefully you've heard this before and you're in third grade or something. You probably went over this. There's three main rock types. There's igneous rocks, sedimentary rocks, and metamorphic rocks. Igneous rocks you can think of as simply as volcanic rocks. Sedimentary rocks are the rocks that are deposited in layers. And metamorphic rocks are kind of these rocks that have been squished and reconstituted. So let's talk about how you can get one rock from the other, because there's all these arrows pointing all over the place, because you can get igneous rocks from sedimentary rocks, you can get igneous rocks from metamorphic rocks, you can get metamorphic rocks from both of those, and etc., etc. But let's look at it like this. So you could take an igneous rock, a metamorphic rock, or a sedimentary rock, and if you melt it back into a magma or lava, and then cool it, you will get an igneous rock. Let's start again. If you have an igneous rock or a metamorphic rock or a sedimentary rock, and you heat it up and give it some pressure, but not enough heat or pressure to melt it, but enough that you kind of start to reconstitute things, the rock will begin to recrystallize, and you will get a metamorphic rock. So heat and pressure to any rock, and you could potentially get a more metamorphic rock. Melt and cool any rock, and you get an igneous rock. And then the third one is if you take any three of these rocks, you weather them, which means you just break them into pieces. You erode them, which means you transport those pieces somewhere else. And then you deposit them, you'll get a sedimentary rock. So that is the basics of Chapter 1 and plate tectonics and a little bit of the rock cycle. What we'll move into next is start talking about what makes up these rocks, which are minerals. So that's kind of Chapter 2, and we'll jump into looking at minerals in the next class period.